So this is our project presentation. My name is Christian Chavez.
I'm Sad Yan.
Jonathan Grant. We're Lab Team 6, ChemLex.
So before we actually begin our presentation on our project, we'd like to emphasize that our endeavors are geared towards the satisfaction of the client. And this is accomplished through quality within our product, how often we can deliver this quality through reliability, and through how many routes we can go as far as providing said quality through versatility. So among all the problems that were presented to us during our project, our team decided to sum it up to the most essential that were important to our project personally. And those included the production as much energy as possible, as consistent as possible, doing it through wind and hydro sources, making sure that it is portable and easy to relocate from place to place, and have it be aesthetically pleasing to whatever environment it is placed in.
As you see here, we have utilized a planetary gearbox in our transmission of mechanical power and generating to electrical power. And that system doesn't exist on the wind and the hydro as we had anticipated in the beginning. So you'll see that there's going to be a planetary gearbox here. In the prototype, we've used a simple pulley system to demonstrate the turning and generation of power there. The final product, of course, everything will have its own big, funky metal gearbox. And then on top of the entire project, something you might be expected to see in the solar farm, that's an attachment that can be utilized depending on whether the placement of this is between high rises or not. So you won't see that as part of the final presentation. Some of the calculations we used, we did a motor test here. This is a power curve, run as a generator, of course, so you're used to seeing a power curve of a motor when electrical power is applied to it, how much RPM does it produce. But here we ran it backwards and we put it on a variable speed drive, and in the beginning we were testing at lower RPM, on a drill 500, 900, and somewhere around 15, 1600. And you can see we got up to around 100 watts output power based on a 1 ohm resistor and a certain voltage out. But then we threw it on a larger RPM source just to test it to see in the real life application how would a motor act that's rated for 24 volts, can we get more out of it? And when we drove it at 4,000, we were running out over 1,000 watts of power. We will go up to 15,000, what you don't see on the graph. It's something that will make the graph really small and hard to see, which is thousands and thousands of watts. Now, this doesn't happen unless you can transmit it and get the RPMs out of your source. So we start with 20, 40 RPMs, and we have to use a gearbox to transmit that power. So we started with an initial state and graphed it and tried to see what kind of load intensities we get on the gears themselves. And then we did an optimization, and finally we came to this. Through this process, we ran into errors, and you see these weird graphs that oversized crowning of the gears, too much meshing, stuff like
that. So this is the list of items that we used in our budget. Since we were using a lot of gears in our project, we tried to focus on getting plywood and laser cutting that in order to decrease our overall cost. At until it eventually evened out to $39.8. So we were dedicated to getting a model that acts as close as possible to the final prototype in terms of power, which is why we got such a high budget. Relatively.
So this was our first day at the project build. As you can see, everything looks pretty rudimentary. At this point, we haven't run into any major problems, as you will see in project build 5 through 6. At those times, we found out that we had a problem with friction as far as the gears go. But at this point, it was everything was pretty rudimentary, and we were just trying to get our design into practical terms as far as the build goes.
So our third and fourth build days, we focused on finishing the window. So we laser cutted the parts of the overall structure, and we got the base finished up in construction. And finally, we constructed actual wind blades and had some wax paper in order to get the maximum coverage.
And as mentioned, everything took off in days 5 to 6. We ran into more problems, which it's a build day.
So this is our decision matrix, where we weighted 3 different designs until we eventually got our current design, which is design number 1. Because even though it has a higher cost, its power output was exactly what we needed. So for our design justification, we weighted the real-life applications in terms of planetary gear systems, which are found in automatic transmission vehicles. So for the purpose of maintaining torque, we want to convert low input RPM to high output. And hydroelectric turbines and downs, where we emulated our wind turbine at in terms of vertical axis blades in order to generate rotational energy into electrical energy.
And this all fancy product that you're going to see is going to be a source of inspiration for the city. It's going to symbolize the success that everybody's driving to achieve in life. It's going to be it's going to give a sense of cohesiveness because everything's coming together in the workings of a team. So you've got a bunch of team players, you've got sports teams, you've got people working together in their businesses. And this symbol is going to be in the middle of the cities, showing that even our power can work together.
And these are the references that we use for our presentation.
And that's our presentation.
All right, thank you.